Hello, everyone. Thesis our CVPR work, a unified HDR imaging method with pixel and patch level. Recovering a high dynamic range image from a series of low dynamic range images with large foreground motions and saturation is challenging. We propose a hybrid HDR deghosting network, called HYHDR-Net, to learn the complicated relationship between reference and non-reference images. Following the alignment fusion pipeline, the proposed HYHDR-Net consists of a content alignment subnetwork and a transformer-based fusion subnetwork. To achieve mutual guidance between patch level and pixel level, the alignment step leverages a gating module to sufficiently swap useful information both in ghosted and saturated regions. We then adaptively merge information with local and global viewpoints. Finally, the proposed method obtains approving results. As we know, HDR imaging can effectively recover details in static scenes. It may produce ghosting artifacts on dynamic scenes or handheld camera scenarios, especially when saturation and motion exist simultaneously. In this paper, we try to generate ghosting-free HDR image in this situation. Following the alignment fusion pipeline, existing methods often use attention to align and convolutional neural networks to fusion. However, these methods only consider the features in the same positions with pixel level and cannot obtain global information. Inspired by patch-based method of the traditional method, we can use similar patches to complete the content of saturated regions. However, patch-based methods have low patch utilization ratio and high computational complexity. In addition, the results of patch-based method often have obvious artifacts in the edges. From the data analysis, we find that patch-based and attention-based methods provide complementary visual information. Thus, this provoked us to design a unified HDR imaging method with pixel and patch level. The proposed HYHDR-Net consists of a content alignment subnetwork and a transformer-based fusion subnetwork. The content alignment subnetwork removes ghosts and generates content of saturation and misalignment. The transformer-based fusion subnetwork aims to generate high-quality ghost-free HDR images from the extracted features of LDR inputs. Considering that the missed content can be filled up using the information of neighborhood regions from the non-reference image, the PA module can search and assemble similar patches to complete misaligned or saturated regions, and the GA module is a complementary branch that removes ghosting with pixel level. The content alignment subnetwork first extracts shallow features from LDR sequences using 3 individual convolutional layers. Then the features utilize patch aggregation and ghost attention modules to separately aggregate useful patches from non-reference LDR images for complex cases and identify the misaligned components for easy cases. To take full advantage of these 2 modules, we use the gating module to recover both contents of saturated regions and sharp edges in motion and saturation. The transformer-based fusion subnetwork aims to generate high-quality ghost-free HDR images from the extracted features of LDR inputs. We first utilize the features extracted from the content alignment subnetwork as input, then use several SWIN transformer layers and deformable layers to model long-range dependencies and dynamically merge useful information with a larger receptive field. To evaluate our model, we perform quantitative and qualitative experiments comparing with several state-of-the-art deep learning-based methods. As shown in figure, these 2 datasets have some challenging samples that cover a large area of foreground motions and over and underexposed regions. Due to intractable large motion and occlusion, most comparing approaches produce ghosting artifacts in these areas. Kalantari's method and deep HDR cannot handle the motion of the background due to error-prone alignments which cause undesirable ghosting. Since NHDR-R and HDR-GAN do not have explicit alignment, they cannot recover the details in the saturated areas. AHDR-Net and AD-Net also suppress some useful neighborhood information and cannot reconstruct large motion. APNT generates ghost regions and blurred edges because of the limitation of the patch-match strategy. Without patch-level alignment, CAVIT also produces ghosts. The proposed HYHDR-net not only integrates several similar patch features to complete misaligned or saturated regions, but also recovers sharp edges in motion or saturation. We compare the proposed HYHDR-net with other approaches on Terson's and SEN's datasets, which do not have ground truth. As can be seen, most methods cannot recover the large area of saturation region and large motion. The halo effect of the sun is evident in the results of other methods, causing saturated ghosting artifacts. The overexposure problem also exists in the figure. Because the gating module can leverage both patch-wise aggregation and pixel-wise ghost attention, HYHDR-net can generate pleasing ghost-free results. The quantitative results for the proposed HYHDR-net on two datasets are shown in table. We show that the improvement of HYHDR-net is very obvious against other previous SOTA methods. HYHDR-net surpasses the second best methods by 0.32 dB, 0.29 dB in terms of PSNR-mu and PSNR-L on Kalantari's dataset, and it also improves by 0.36 dB and 0.74 dB in terms of PSNR-mu and PSNR-L on WHO's dataset. Overall, the proposed HYHDR-net achieves state-of-the-art performance consistently on all 5 metrics of 2 datasets. We conduct ablation studies on Kalantari's dataset, and validate each proposed module in HYHDR-net. Patch aggregation and ghost attention improve the performance. With gating, the performance is further improved. The full model obtains the best numerical result. All components can improve the performance.